Alright, curve sketching. This should be the easiest thing in the world. Oh wait, actually no, it's not curve sketching. It's applications of differentiation. So we're going to go over something called optimization. And simply put, optimization is just trying to get the most or the least out of something. So making sure something is optimized or that something is going to yield you the maximum results of what you want. So notice I say the word maximum, and the reason I say the word maximum is because it's literally just the first derivative test. We're just checking for maxima and minima. So I'll give you an example. Now there's a few steps. I'm just going to read them. I'm not going to write them out. It's understand the problem, which is obvious. Draw the diagram. Define an equation based on a variable for which you want to optimize. And then the other ones are just like, I don't know why they do it. I mean, seriously, like if I wrote a mathematical textbook, I would not include any of um, this complicated language. I mean, I'm sure there's math books that are a little bit less covering than this, but they say like express Q in terms of their symbols, which is like quantity. But I would just skip all that and just explain what it is in the general sense. So what it is in the general sense is, again, just trying to maximize something and trying to find the optimum. Now the optimum is simply just the position in which you'll get the maximum output or minimum output for whatever you put in. So I'll give you an example. So let's say you have let's say, I could define it a bunch of different ways, but let's say you have a house here, and this is going to be your house. I'll label it house, and here we have a fence. Actually, let's probably make it like this. And let's say that the perimeter of the fence is set to 40 feet, which essentially means that you only have 40 feet of this outside material. So you can rearrange this how many ways you want. Here it probably looks around maybe like 20, 10, 10. You can probably make it even steeper, like 5, 35. But essentially, you want to find the thing that maximizes the area so that you can have, I don't know, whatever you want to put inside this fence. So how would we do so? Well, let's remove the diagram and let's draw a smaller one so that I can show you the mathematical framework. So we have the house and we have the fence. So let's just denote one side of the fence x and this side y. So we see that we have two x's and y, which is essentially equal to 40. Now, don't think of this as a system of equations. While it technically is, just think of x and y as arbitrary variables. So 2a plus b, that's essentially all math is, or algebra in this general state. So that means 2x plus y equals 40. So that means if we increase x, or like let's say x is 10, that becomes 20, and that means y is also 20, which equals 40, which essentially means that this is 20, that is 10, and that is 10, because we just plugged 10 into here. So essentially, we're just trying to find the optimum, and that's the first step. So yeah. So now we have to define the area formula, and thankfully for us, we're just given a simple rectangle, which is length times width. So the length is just going to be x, or this first quantity, times y. And you can see that mathematically and geometrically and visually right here, that x times y will just give you this area. The reason why we have 2x in the perimeter is because this also is needed for the fence material. So this is not a function, and it's not a function for two reasons. Well, first, there's three variables in here, and second, well, yeah, I guess there's only one reason. It's just not a function of one input. So how do we get the other input? Well, notice that we can rewrite y in terms of x, such that y is a function of x. And once we know what that is, we just plug it back in to get x 40 minus 2x. Now, you can expand this out. I'm going to do so here, 2 minus 2x squared plus 40. So calculus wants you to use the first derivative test. But, I mean, I guess you could use vertex formula here, which would essentially state that the optimum is at x equals 0. But let's use the calculus test because it wants you to. So this means this is the area formula in terms of x. That means whatever x is, this will give you the area. So you just completely, well, you didn't eliminate y. It's still in here, but it's just expressed in terms of x. But you completely just took y out of the equation. Or I mean, not completely. I guess you just took the letter y, or the variable y, out of the equation. So if this is the area formula, we want to find the maximum or minimum here. This one opens downwards, as you know. So the minimum would theoretically be just 0 because it's I can use the quadratic formula, but the quadratic formula uses the derivative anyways. So applying the power rule here, we get negative 4x, and we set it equal to 0. Logically, if we drew out the number line, we have 0, negative, infinity, infinity. Past 0, it's negative, and past below 0, it's negative. So that means there's a maximum at x equals 0, which we already knew. We plug that back in. So area equals negative 2 times 0 squared plus 40, which just yields an area of 40. So we realized the maximum is actually a square because we can also solve for x if we plug it back into here. So if we plugged it back into there, we get... actually, wait, hold on. Yeah, wait. Hold on. Okay, so we know it's 40, which essentially means that the max area is 40. So then we could do 40 equals x times y. And then once we plug the x back in, we can solve for the perimeter formula. So essentially, the area is maximized when x is... Wait, hold on. Doesn't make any logical sense. Oh, I know where I'm wrong. I forgot to distribute properly. I was like, what? There's no way that the maximum area is when x is equal to 0, because that would mean there's no fence at all. So let's go back here. That was my crucial mistake, but it's simple again, just chain rule and figure it out. So it's going to be negative 4x plus 40. Solving for x, we get x equals 10. I just did that algebraically in my head. So we get 10, infinity, and negative infinity. And note that whenever the function is equal to 0, that's the only changes, or the place where sign changes could occur. So past 10, it's going to be negative. Below 10 is positive, which is kind of logical because you have to assume a maximum. If this was swapped and it's negative this way, then that would be a minimum area, and that would be impossible to find. So that means the maximum occurs when x equals 10, and if we plug it back into the area formula, we get, well, I could probably do the math in my head, negative 200 plus 400, which is equal to 200 feet, and that would essentially equal when this is 10 and this is 20. Yeah, wait, when that is 10 and that is 20. Oh, sorry, when that is 10 and this is 10, so this is also just 100 feet. Let me see. Oh my God. Wait, 10, 20. Yeah. So this is the optimum here. And it's essentially when x is equal to, or when the sum of these sides are equal to this side here, which is essentially just kind of like not a square, but a rectangle where one of the lengths is one half of the other. So that's where you'll typically find the optimum in reference to that. So let's try a different one, because I think I just made a crucial mistake. So let's start with the... let's start with a river. The same exact problem, but just worded differently. And this is the river here. What are the dimensions of a field that you want to put by the river that gives you the largest area? So this is going to be the river here. So how would we get the largest area? Same thing here. Let's assume that the perimeter is equal to 2400. So essentially you only have 2400 of these sides here, which is kind of stupid because in what world do you have 2400 of that? I mean, it would only make sense if there was like a fence or something, but I mean, still, you can still apply the logic here. X times y equals area. That would mean that if you solve for y, I mean, you could technically solve for x too, it wouldn't make a difference. But it's going to complicate things a little bit. So we do y equals 2400 minus x divided by 2. So we plug that back in, 2400x, or minus x divided by 2. And then you differentiate both sides. So a prime is just going to be equal to 2400 minus 4y, which means that, or 4x, which is essentially when x is equal to, hold on, 100 is x, 200. Okay, so that is equal to 1200 x minus x squared over 2, and differentiating it, we get a different equation. So 1200 um, minus just x. So that means x is equal to 1200, which means that it's maximized when y is equal to 600, and essentially that the sum of these sides are equal to here. So it's maximized where you have 1200 and 600, and you can plot it on a graph and see that there is no other area you can get with there's no higher area you could get with a similar perimeter. So that's essentially all that is. Um, Essentially, finding the optimum is just finding the maximum or minimum using two functions that typically differ in variables. So again, the idea is if you're given the area, for example, and that's like length times width, and it asks you to find the maximum perimeter given a fixed area. So let's just say that's like 20 equals length times width, and you have a perimeter which is equal to, well, it depends. If it's a square, then it'd be 2L plus 2W. Well, that would, yeah, 2L plus 2W. So we're assuming it's a rectangle, LW. Then you're essentially just finding the maximum perimeter that you can get for that given area, and vice versa. You can apply that to everything. You can actually apply that to economics. You could apply that to anything that you want to. So that's what I find kind of interesting about this lesson, is that it's actually practical, and it's really easy. It's just first derivative test applied. And it's kind of funny because they never use the second derivative test, although they make us learn it. So, I mean, that's pretty illogical to me, but I guess that's how the book does it. So.